Today we will discuss our new topic, that is classification of elements and periodicity in properties. In this topic, first we will discuss what is the need of classification of element. As we know that elements are the basic component of all types of matter. At the beginning of the 18th century, only a few elements were known. During 18th and early 19th century, advance in chemistry made it easier to isolate elements from their compounds. As a result, the number of known compounds or known elements had more than doubled from 31 in 1800 to 63 by 1865. At present, 114 elements are known. Out of these recently discovered elements are not natural but synthetic, that is man-made, and efforts are still going on to synthesize new elements by artificial transformation. As the number of known elements increased, it became rather impossible to study individually the chemistry of these elements and their compounds, and scientists began to investigate the possibilities of classifying them in useful ways. The basic object and need of classification can be best stated in the words of the actual or ideal arrangement together of those which are alike and separation of those uh, that are alike. The purpose of this arrangement being primarily to disclose the correlation or law of union or properties or circumstances and to consider the operation of the mind in clearly receiving and then retaining in the memory the characteristic of the objective in questions. In short, it can be said that the basic object of classification is to arrange the facts regarding elements and their compound in such a way so that we may have greatest control over their characteristic, least possible effort. The best classification would be one which put together those elements which resemble in most respect and separate others. So time to time, different elements, different scientists have been proposed the views for the classification of elements. So first we will discuss early attempts. Early attempts to classify elements first is given by the Lavoisier in 1803. Lavoisier classified the element into two categories, that is metals and non-metals. This classification of elements depend upon their properties, but some elements are such dual nature. Means some elements have both properties, metals and non-metals. So this classification is discarded. Now second classification is given by Dauvergne. To classifying the element, Dauvergne gives a rule which is called Dauvergne's tide. Dauvergne given this rule in 1817. Dauvergne, a German chemist. Dauvergne gave his law of tides, according to which in certain tides, in his group of three elements which have similar chemical properties, the atomic mass of the central element was the mean of the atomic mass of the other two elements. It means the properties of the middle elements were in between those of the two elements. For example, first tide of Dauvergne is lithium, sodium, potassium. Atomic mass, the lithium is 7, potassium is 39, and according to Dauvergne tides, the atomic mass of the middle element, that is sodium, is the mean of the two elements, that is 7 plus 39 divided by 2 equals to 23. It means property of the sodium is between of the properties of lithium and potassium. Similarly, Second triad, that is chlorine, bromine, iodine. Atomic mass for the chlorine is 35.5 and iodine is 127. So the atomic mass of the bromine is 35.5 plus 127, which divided by 2 equals to Pr, its atomic mass equals to 81.25. It means properties of the bromine is between chlorine and iodine. Similarly, third triad, calcium, strontium, barium. Atomic mass of the calcium is 40 and barium is 137. So atomic mass for strontium is 40 plus 137 is divided by 2, it becomes 88.5. For the drawback is Dauvergne triads is not applicable for all the elements. For example, Dauvergne triads, that is Fe, cobalt, nickel. All these three elements have almost same atomic mass, that is iron is 56 and cobalt is 58.93 and nickel is 58.69. Similarly, next is Ru, ruthenium, rhodium, Rh and palladium, Pd. These three elements also have almost same atomic mass, that is ruthenium is 101, rhodium is 102 and palladium is 106. Next triad, that is osmium, iridium and platinum. Mass of the osmium is 190, iridium is 192 and platinum is 195. So we can say that Dauvergne triads is not applicable for all the elements, but merit of this triad is on the basis of Dauvergne triad, it becomes clear that properties of the elements have some relationship with their atomic masses. Properties of the element with their masses. Now next attempt or next classification done by the Newland. That is called Newland's law of octaves. It was done by 1864. Newland is an English chemist. John Newland proposed a new systematic of grouping elements with similar properties. He tried to correlate the properties of elements with their atomic masses. He arranged and then known elements in the order of increasing atomic masses. He started with the element having the lowest atomic mass, that is hydrogen, and ended at thorium, which was the 56th element. He observed that every 8th element had properties similar to that of the first. So basically, Newland's law of octaves depend upon musical notes. As we know that musical notes follow the order. Newland's law of octaves basically depend upon musical notes like this: sa, in English, do, re, in English, again re, ga, in English me, ma, in English fa, pa, in English so, tha, in English la, ni, in English ti. So sa, re, ga, ma, pa, dha, ni, and again sa. So we start numbering from 1, 2, 3, 4, 5, 6, 7, 8. So it has been clear that every 1 and 8 same. Like in musical notes, Newland arranged elements according their increasing atomic mass and find that every 1/8 element have similar properties. For example, hydrogen, its atomic mass is 1, lithium, beryllium, boron, sodium, magnesium, aluminum, silicon, phosphorus, sulfur. Now chlorine, potassium, calcium, chromium, titanium, Mn, iron, cobalt and nickel, copper, zinc, yttrium, indium, arsenic, selenium. So the properties of hydrogen, fluorine, chlorine are same. Similarly, the properties of lithium, sodium and potassium are same. The properties of beryllium, magnesium, calcium are same. And the properties of boron, aluminum are same. Carbon, silicon are same. Nitrogen, phosphorus are same. Oxygen, sulfur are same. But now we will discuss the drawbacks of Newland octaves. The first drawback of Newland octaves that no space was left for the elements which were unknown at that time. And second is the law of octaves was found to be applicable only up to calcium. It was not applicable to elements with higher atomic masses. And next is Newland placed two elements in the same slot to fit elements in the table. He also placed some unlike elements under the same slot. For example, cobalt and nickel are placed in the same slot and in the column of fluorine, chlorine and bromine. But cobalt and nickel have properties quite different from fluorine, chlorine and bromine. Similarly, iron, which has resemblance with cobalt and nickel in its properties, has been placed far away from these elements. So it was realized that Newland's law of octaves work well only with lighter elements. Therefore, this classification was rejected. Now, next classification given by Lothar-Meyer. Lothar-Meyer classification depends upon practical approach. It was given in 1869. Lothar-Meyer in Germany and Mendeleev in Russia quite independently evolved in 1869 identical classification of elements. Both these classifications emphasize the periodicity of the elements with their atomic masses. But Mendeleev classification was based largely on consideration of chemical properties, and the Lothar-Meyer classification depend upon basically physical properties of the elements. Lothar-Meyer presented the classification in the form of curve, while Mendeleev in the form of a table. Lothar Meyer calculated the atomic mass volumes of the known elements by applying formula, that is atomic volume equals to atomic mass upon density. When he plotted these atomic volumes against corresponding atomic masses, a curve taking the form of sharp peaks and broad minima was obtained. Now, we will draw the curve of Lothar Meyer. In this axis, you will take atomic mass AMU. In this axis, taking atomic volume. Lothar Meyer pointed out that elements having similar properties occupy similar positions on the curve such that first is alkali metals, that is lithium, sodium, potassium, rubidium, cesium, having the largest atomic volume occupy the maxima of the curve, that is here is lithium, sodium, potassium, rubidium and cesium. Second is the alkaline earth metal like magnesium, calcium, strontium, barium occupy position at about the midpoints on the descending portion of the curve. That is, the position of alkaline earth metal is that. That is the mid position. Here is the magnesium. And here is the calcium. And here is the strontium, magnesium, calcium, strontium. And here is the barium. All these called alkaline earth metal. And the third is the halogens, that is fluorine, chlorine, bromine, iodine, occupy position on the ascending portion of the curve before inert gases. So the position of halogens in the curve is that here is the chlorine, bromine, the iodine. Now fourth is the transition elements, that is d block elements occupy minima of the curve. That is the position of the transition element is that there is the cobalt and the copper. Now here is this RH, rhodium. On the basis of above observation, Lothar Meyer proposed that the physical properties of the elements are a periodic function of their atomic masses. Now, merits of Lothar Meyer. After Lothar Meyer, later on when atomic numbers of the elements were plotted in place of atomic masses, the general patterns of the curve retained the same. Now, demerit. It was an ideal classification but lacked in the practical utility as it was not easy to keep in mind the different portion of the curve.